Hi, welcome to our next chapter. This chapter is going to deal with aqueous ionic equilibrium. And in this chapter, we're going to look at several different processes. So we're going to look at acid-base chemistry. We're going to expand upon what we learned in the last chapter. We're going to look at ionic compound solubility. And so we're going to move past those sort of black and white solubility rules and look at the equilibrium systems that are actually in place when you have an ionic compound in solution. And then we're also going to look at complex ion formation with transition metals. So we're going to look at transition metal ion complex formation. And so all of these seem very different, but they all have one thing in common in that they're equilibrium processes. And so this is just kind of a continuation of the last two chapters that we've talked about. The first chapter was just plain equilibrium. The last chapter has been acid-base equilibrium. And now we're going to kind of end our series here applying equilibriums to various different systems. So you're going to see a lot of the same types of calculations, but we're going to be expanding upon that significantly in this chapter. So some of the objectives that we have for this chapter. We're going to first look in this first part at buffers. And so buffers are important. Buffers are important for us from a biological standpoint because they keep our blood at a constant pH. And buffers are really unique systems that you design. So buffers don't just happen automatically, and buffers aren't always necessarily there. It's something that you have to make happen. So you're going to put together your strategy for what the pH range around that buffer that you want to buffer and what the components of that buffer are going to be. So we're going to talk about buffer range and buffer capacity. We're going to talk a little bit about calculating the pH of a buffer, and I'm going to introduce a new equation to you. But like I said, we're not going to do a lot of calculations in these pre-recorded lectures. We're going to come together in our synchronistic Zoom meetings and do our calculations there. And we're also going to learn what happens when you challenge a buffer. So I have a buffer system. My buffer is made to resist pH change when I challenge it either with an acid or a base. And so we're going to learn what that means and how to recalculate your pH after you've had an acid-base challenge to a buffer. And then we're going to lastly learn about titration indicators. And so acid-base titrations are neutralization reactions. And you've been doing these all along in your chemistry career most likely. And you probably use phenolphthalein, which is like a pink indicator that you used in some of your basic acid-base titrations, but there's a lot of indicators. So we're just going to briefly touch on these organic dyes that we use for pH titrations. So those are our objectives for today. We have quite a bit on our plate. So without further messing around, let's talk about buffers. So like I said, a buffer is something that we're going to design. And buffers have a pH that's driven by the conjugate acid-base pair that makes up the buffer. So that whatever I decide on in terms of my conjugate acid base that I'm going to use to make my buffer, that's going to drive the pH. So I can design a buffer around any pH that I want. I just have to be selective in my conjugate acid base pairs that I select for it. So buffers will resist change when challenged by an acid or a base that's been added to my solution. Buffers have a range, a pH range, and they have a capacity to buffer. And so we're going to talk about all of these components. So my pH range is going to be a range that is above and below the pH of my buffer, and we'll talk about that. My capacity is going to deal with how much of my conjugate acid and conjugate base is present. That's going to affect the capacity of my buffer. So the more of these I have in terms of concentration, the larger the capacity of my buffer is that I'm going to have. And then we're going to look at resistance pH when I challenge it by an acid or a base. And these would be acids or base that you add to the buffer. So I'm going to make the buffer with a conjugate acid-base pair, and then I'm going to challenge that buffer by adding either an acid or a base or both of them to that buffer. So my pH is driven by this conjugate acid-base pair. So if we look at how to create a buffer, I'm going to find the pH range I want to buffer the solution to. Then I'm going to select my conjugate acid-base pair for that range. I'm going to make my buffer with amounts of both conjugate acid and conjugate base added. And ideally, I want equal amounts and lots of both of them. That's going to give me the best buffer that I have. I want large concentrations of both conjugate acid and conjugate base, and I want similar concentrations of both conjugate acid and conjugate base. So when I make my buffer, when I create this buffer, I'm going to first figure out what the pH range is around that I want to buffer. Then I'm going to select my conjugate acid-base pair for that range, because not all conjugate acid-base pairs buffer in the same range, which is good. And then I'm going to make my buffer by taking amounts of both the conjugate acid and the conjugate base and dissolving those into solution. Acetic acid is C2H3O2, and it's made from this acetate polyatomic ion. And I have my ionizing hydrogen here. So if I have acetic acid in solution, and I'm just going to add water here, it's going to be in equilibrium with hydronium ion and the acetate polyatomic ion. So if I just take acetic acid and I dissolve it in water, I'm going to have this equilibrium system here. This is going to have a relatively small Ka. If I were to write my law of max action, my Ka would look like this, with hydronium ion concentration, acetate ion concentration over my undissociated acid. And this would be my Ka. So if I just plugged in that I had 0.150 molar of acetic acid, I could calculate the pH of that solution, because I would have a equilibrium scenario where I could plug it into my Ka here. That would be kind of last chapter. And in this scenario, my assumption is that I'm starting out with none of this acetate ion. So my assumption is if I have this initial concentration, I'm going to produce a little bit of hydronium ion, a little bit of acetate ion. My assumption is I'm going to start with neither one of these. When I make a buffer, my conjugate acid-base pair, first off, let's look at our conjugate acid-base pairs here, right? So this is my conjugate acid, and this would be its conjugate base. So remember, my acid is going to donate a proton, my base is going to accept a proton. So if I have a conjugate acid-base pair, the difference between them is this ionizing proton here. So this is my conjugate acid-base pair here, and this is going to be a conjugate acid-base pair here. I'm not going to worry about water too much. What I'm looking at here is my weak acid and its conjugate base. So if I wanted to make a buffer, and I wanted to make a buffer using acetic acid, I'm going to start by adding in amounts of both of these. So I'm going to have initial concentrations of both of them. So I'm not going to just start with acetic acid and have a little bit of acetate ion, because my Ka is so small, I'm going to force this equilibrium in a way that I have appreciable amounts of both of these. So I'm going to start with both of these. These would be my conjugate acid, and this would be my conjugate base, and I'm going to add in large quantities of both of them. That's going to create my buffer, because now I'm going to have a system where I have a large amount of this and a large amount of this in solution. And then that is going to allow me to effectively buffer against pH change. If you look here, this is just showing this with acetic acid. So what I'm adding here is, this is my weak acid, so this is my acetic acid, and this is the conjugate base. And I'm not just going to have acetate laying around. I'm probably going to have acetate in a part of an ionic compound. And remember, your acetate ion is highly soluble. So whatever metal it's associated with here, when I add it to water, those are going to break apart. And so I'm going to have free acetate ion. This metal is just going to be a spectator ion. It's not going to be involved in anything that's happening in that buffer solution. And so my components here that I'm going to be looking at are the fully undissociated acetic acid that's coming from the weak acid part, and the acetate ion, which is coming from my sodium acetate solution. And I'm going to mix those together in large amounts, and so that's going to create my buffer. So what's going to happen with this buffer? Buffers can be really complicated at first. If you just kind of break it down into, there's only two things that can happen in a buffer. Is you can have an acid added in, or you can have a base added in, and those are going to behave predictably. So I'm going to go back to my acetate buffer here, but now since this is a buffer, I have appreciable amounts of both of these. So I have a buffer, I have a significant amount of my conjugate acid here, and I have a pretty significant amount of my conjugate base, and that's going to make up my buffer. So what happens if I add an acid? to the solution. What is HCl going to react with in the buffer? If I'm forming this, and remember if HCl is a strong acid, then this is essentially H plus that I'm adding in. What is H plus going to react with? Well, H plus is not going to react with my conjugate acid because it's not going to pick up another hydrogen. It's not going to really react with water here, but it can react with my conjugate base because remember, I have a lot of this present. I have a lot of this present and I have a lot of this present. So when I add in H plus, my buffer is going to work by my conjugate base is going to react with the hydrogen ion here. And what that's going to do is it's going to shift and I'm going to start producing more of my conjugate acid. So if I add in H+, what's going to happen is my H+ is going to react with my conjugate base. This is why I need this in a large amount. And it's going to produce HC2H3O2, which is my conjugate acid. So when I challenge my buffer with an acid, I'm basically reacting with the conjugate base that's in that buffer, and I'm going to be producing more of this. So when I add my acid, I'm going to see this concentration is going to decrease because it's reacting with the acid, and this concentration is going to increase because I'm producing it. And as long as I have a lot of this and I'm not adding too much acid, so this is going to allow me to buffer the pH here. So I won't have a big change. I might see a little change in pH, but I'm not going to see a huge change because if you think about it, this is a strong acid. So if I just have this present and I add this in, the pH is going to go down a lot, and it's going to go down significantly because whatever the hydrogen ion that's being produced from this is going to swamp whatever this is that's here. But if I have a lot of this present, it's going to step in and it's going to react this hydrogen ion before it's able to really drop the pH, and then I'm going to see a little bit of it drop in pH because I'm increasing my weak acid. So it's going to have much less of an effect. So that's what happens if I challenge my buffer with an acid. If I challenge it with a base, so let's say I add in hydroxide. So let's say I add in NaOH. This is going to be adding in OH minus into my solution here. And I want to know, what is my hydroxide going to react with in the buffer? Now remember, the things that I have in solution, I have my acetic acid, I have water, I have hydronium ion, and I have my conjugate base. So if I add in hydroxide, hydroxide is going to react with my hydronium ion here, and it's going to produce water. And what that's going to do is that it's effectively going to shift this reaction. So if you think about Le Chatelier's principle, if I remove a product, it shifts the equilibrium of that reaction forward. And so by adding hydroxide, I'm going to neutralize it with my hydronium ion, but that is going to shift this reaction so that I'm going to start disassociating more of my acetic acid. So it's less of a direct effect and a little bit more of an indirect effect. So this up here was more of a direct effect. Hydrogen ions reacting with my conjugate base, and I'm going to produce my conjugate acid. Here I have more of an indirect effect where my hydroxide that I'm going to add in is going to react with the hydronium ion and produce water, and then that is going to effectively shift the equilibrium of this reaction because I'm taking this out forward, and I'm going to end up as a result, I'm also going to produce C2H3O2 minus, and I'm going to use up some of my conjugate acid. So what I'm going to see is I'm going to see my conjugate acid is going to decrease and my conjugate base is going to increase. And so that's going to be the effect if I challenge my buffer with a base buffer challenge. And if you think about it, if I just dumped a bunch of base in with a weak acid, it's going to kind of flood that system, and I'm going to see a significant increase right away in my pH that's driven by this hydroxide because this is a strong base. But if I have a buffer, I'm not going to see that because I'm going to have appreciable amounts of this present, and this is going to quickly neutralize my hydroxide, and then I'm going to see a small increase in my buffer pH because I'm producing a little bit more of this acetate ion and I'm decreasing my weak acid here. So both of these, my conjugate acid and my conjugate base, are going to affect the pH of the buffer. And then if I challenge, so these would be a scenario where I'm challenging my buffer, I'm going to be changing the concentration of this. I'm going to be either increasing the concentration or decreasing the concentration of these two components when I challenge that buffer. So I can keep track of the pH of my buffer, and I can also keep track of the pH of my buffer when it's undergone a challenge through one single equation. It's a one-size-fits-all equation. This is called the Henderson-Hasselbalch equation. And this is going to effectively relate my concentrations of my conjugate acid and my conjugate base. So at no point ever am I going to add in the acid or base that I'm challenging my buffer with. This is always going to be looking at these concentrations here. So this equation, but it only looks at the conjugate acid-base system that's within the buffer. And so try to keep that in the back of your brain when you're working through these problems. Before I give you this equation, I want to talk about Ka and pKa, because in this chapter, we're going to move away from looking just at Kas and we're going to look at pKas. And a pKa is simply the negative log of the Ka. Just like pH is the negative log of hydronium ion concentration, pKa is the negative log of Ka. I can also apply this to Kb. So pKb is equal to the negative log of Kb. And then I can actually apply these two together, since these are related by these log systems, that pKa plus pKb equals 14. Just like pH plus pOH equals 14. So these might be nice things to just kind of have handy to think about these relationships. And then also I can toggle back and forth between Ka and Kb this way, and we did this in the last chapter, is my ion product constant for water, which is 1.0 times 10 to the minus 14th at 25 degrees, is equal to Ka times Kb. So if I have a Ka and I want to know a Kb, I can use this equation to get back and forth. If I have a Ka and I want to know the pKa, I can take the negative log of that. So these are always going to be positive values. So when you're taking the log, you're always going to take the negative of the log because the log is going to give you a negative value out. So if I go back to that Henderson-Hasselbalch equation, to calculate the pH of a buffer, I'm going to use this equation here. I'm going to say the pH is equal to the pKa plus the log of my concentration of conjugate base over my concentration of conjugate acid. So these brackets generally mean molarity, but you can also use moles here. I have to use molarity for pHs, but in this equation, and only in this equation, you can use moles. If you're not sure, just take everything to molarity and then you'll always be right. All right, so there's some conditions for us to use the Henderson-Hasselbalch equation. So I told you I wasn't going to do any calculations, but let's just do a really quick one. Let's say I have a buffer, and we'll go back to our acetic acid buffer. How about that? And let's say I start this buffer and I have 0.150 molar of this and 0.150 molar of that. And I want to know what is the pH of the buffer. I need to know my pKa for acetic acid in order to solve this problem. So if I don't know my pKa, I can look up my Ka and get to my pKa that way. This is where that table from the last chapter is going to be really helpful, because the table, at least for the acids, gives you the pKa values as well. What you'll notice is I have my standard Ka values here, but I also have the pKa. So my negative log of my Ka has already been taken care of for me. So my pKa for acetic acid is 4.74. Now I'm just going to plug everything into this equation. So my pH is going to be equal to my pKa plus the log of my conjugate base. So this is my conjugate base. This is my conjugate acid. My base concentration is always going to go on the top. So in this case, they are the same. And then when I take the log of 1, that's going to give me 0. So in this case, my pH then becomes 4.74. So if my concentration of my conjugate acid equals the concentration of my conjugate base, then the pH of the buffer equals the pKa of the buffer. And that's a nice kind of handy thing to have. If it doesn't, so let's say instead in this scenario, let's say I didn't have equal concentrations of them. Let's say I have 0.140 molar and 0.150 molar. Now I have different concentrations. I still have appreciable amounts of both, so that's good. Now to calculate my pH, my pKa is going to be the same, but now my log ratio here is going to be different. When I work this out, I'm going to get 4.74 plus 0.02996 and so forth. I'm going to add that together. And my pH is going to be a little bit higher than the pKa, 4.77. So not much, but a little bit higher, which I would expect because I'm going to have a little bit more of that conjugate base present than my conjugate acid. So I would expect my pH to be a little bit higher. So I can use this equation to calculate the pH of a buffer. Let's say I have a buffer and I don't make it with a weak acid, I make it with a weak base. So I can also make a buffer with a weak base, and now this is my conjugate base and this is my conjugate acid. And so I'm going to have a Kb for this. I would want to convert that to a Ka, then get my pKa, and then plug it into my equation. So this could be a buffer where I have, this is my conjugate base, and this is my conjugate acid. And if I have appreciable amounts of both of these, then I have a buffer, but instead of being driven by a weak acid, it's driven by a weak base. And then I've added in ammonia chloride or something like that. And that's given me my conjugate acid part of that buffer. So I can have a buffer where I make it with a weak base, or I can have a buffer where I make it with a weak acid. I'm always going to have the corresponding conjugate pair with it. Okay, and like I said, we're going to be doing a lot of calculations with these when we get into the Zoom meetings together. So a couple of things. To have a good buffer and to be able to use the Henderson-Hasselbalch equation, so two conditions must be met to use my pH equation. And they're related. So the first one is that I should be able to use my X is small approximation. You guys remember what that is. So that means that if I have a system where I have an initial amount of this and that is much greater than my Ka, then I can use my X is small because whatever is disassociating here is really small compared to the full amount. My concentration of my initial amounts of both my conjugate acid and my conjugate base must be much greater than the Ka or the Kb, depending upon whether I'm starting my buffer with a weak acid or a weak base. So these initial concentrations much be greater. And so we're looking at something greater than about 10 to the third, greater than or equal to 10 to the third. So if I have that difference, then that's going to allow me to use that Henderson-Hasselbalch equation. The second one is that I have appreciable amounts, so my amount of my conjugate acid and the amount of my conjugate base are not too small. So these kind of go hand in hand. So if these are really small, then I probably can't use my X is small approximation. So I need to have these two conditions met before I can use that equation. So we already talked about what happens if I add an acid or a base to a buffer, how we can use that to calculate the changes. So here I'm going to look at calculating the pH once I've challenged my buffer. So I'm going to go back to my acetic acid buffer. And let's say I add OH. So I'm going to challenge this buffer by adding in potassium hydroxide, which is going to give me OH ion. So what that is essentially going to do is the OH ion is going to react with the hydronium ion. It's going to decrease the concentration of this, which is going to shift my equilibrium. So this is going to shift my equilibrium temporarily forward, which means I'm going to produce more of my conjugate base, and I'm going to react or disassociate more of my conjugate acid. So this is going to go down, and this is going to increase. So how much they go down and how much they increase is based on how much of this I add. So for every 1 mole of base added, this is going to go down 1 mole, this is going to go up 1 mole. So if I add 1 mole of OH, this is going to decrease by 1 mole, and this is going to increase by 1 mole. If I add 2 moles, then this is going to go down by 2 moles, this is going to go up by 2 moles. So I have a stoichiometry problem. Whatever I add in, it's going to decrease this by the same amount, it's going to increase this by the same amount. So the first thing is I'm going to figure out what my stoichiometry event is. We're going to call that a stoichiometry event. I need to first find moles of acid or base added. Then I'm going to subtract and add moles to my conjugate acid and conjugate base. And adding and subtracting is going to depend on which way the reaction is being shifted. And so then I'm going to have new moles of conjugate acid and conjugate base after the shift, and new equilibrium is reached. Then I can use my Henderson-Hasselbalch equation with my new moles of conjugate acid, conjugate base to find the new pH. So those are going to be my steps. So first off is my stoichiometry step, and then I'm going to apply it to my pH equals pKa plus log of conjugate base, conjugate acid to find my new pH. And what I'm doing is I'm trying to find my new concentrations here. This is where I don't necessarily have to put these back in molarity. I can just use moles straight. So when I write the equation for my shift, I want to calculate the mole changes for my conjugate acid, conjugate base. That's the only thing I care about, right, is what's happening here. I'm going to plug that back into this equation and solve. But in order to understand what's happening here, I have to look at the number of moles that I'm adding and seeing how that's affecting. So if I add in hydroxide, my conjugate acid is going to go down, my conjugate base is going to go up. If I instead challenge this with an acid, so if I add in HCl, that means I'm adding in essentially hydrogen ion. That's going to react with my conjugate base, and it's going to shift the equation in this direction. So I'm going to increase, so I'm going to produce more of this, of my conjugate acid, and I'm going to react my conjugate base, so this is going to decrease, and this is going to increase. And the amount that those go down depends upon how much of this I add. So if I add 2 moles of this is going to go down by 2 moles, this is going to go up by 2 moles, and then I'm plugging these new moles back into my equation and finding my pH. So that's how we're going to calculate the pH when we do these challenges. And like I said, we'll do these calculations together in our Zoom meeting. So the last thing I wanted to cover in this part was just talking about some generalizations of a buffer. So how effective is a buffer? So a buffer can be destroyed by adding too much acid or base. So we have a finite amount of acid and base. This is the buffer capacity. And the larger the concentrations, so the larger the concentrations of my conjugate acid and my conjugate base, the more capacity. My buffer is going to be most effective at a pH that is equal to the pKa. Because at the pH equals to the pKa, then my conjugate acid and my conjugate base concentrations are equal to each other. So it's most effective when it's there. But my range can be plus or minus 1 pKa value. So for acetic acid, for instance, acetic acid has a pKa equal to 4.74. So an effective range for a buffer that's made with acetic acid would be 3.74 all the way up to 5.74. So plus and minus 1 pKa value. So this would be the range of this buffer. So if I wanted to buffer my pH to 7, I wouldn't want to use an acetic acid buffer. I would want to use something else that had a pKa closer to 7. If I wanted to buffer around 4, this would be a perfect conjugate acid-base pair to use because my buffer range is right around 4. So this is going to be where we're going to end for today, and then we will come back together and we're going to talk about pH titrations in part 2.